So as it says, we are discussing more about continuous distributions of charge, and the first one we'll be discussing is a semi-infinite line of charge. Semi-infinite line of charge. This is what we are starting with. Now, how can something be semi-infinite? Now, it's just a description I'm using, used originally by the Russian author Irodov. Now, this is a line of charge which goes up to infinity up over there and has an end on this side. So it starts here, goes up to infinity, and since it is finite on this end and infinite here, you can say it is semi-infinite. It has a linear charge density lambda. Lambda is its linear charge density. Now what is that? That is charge per unit length. Now we are interested in calculating the electric field at this point here at a distance, let's say A, from the line of charge. I'm giving you a formula for this without derivation, because we have done the derivation for an infinite line of charge in the previous video, and therefore a derivation for this one is not essential. You can derive the result yourself now using the ideas that I have used in that derivation, if you're interested in deriving, that is. I'm just giving you a formula here. Assuming the lambda charge per unit length to be positive, the electric field here has two components. One component is perpendicular to the line of charge and the other is parallel to the line of charge. Mind you, these two, the formula that I'm giving is workable for a point at a perpendicular distance A from the end of this line of charge. Now, these two components are both equal and have a magnitude lambda by 4 pi epsilon naught A. So they both have the same magnitude. This one is parallel to the line of charge, this one is perpendicular to the line of charge, and the directions that I have indicated are for a positive charge distribution. If the charge here is negative, both directions get reversed. So that's the formula for a semi-infinite line of charge. We are going to take up a couple more cases of continuous charge distributions in this video. This is the first one, and for this one I'm just giving a formula without the derivation. The next couple I'll be deriving. So the next one that we are taking up is a circular arc. I hope you've taken a screenshot here and taken note of this. Now, the next one that I'm taking up is a semicircular arc. Not semicircular, but let's say circular arc. So, we have a circular arc like this one here. Again, it carries a linear charge density lambda Now this circular arc has a radius A, and we are interested in calculating the electric field at its geometric center. The angles here are alpha each, and we'll be calculating the electric field at the geometric center of this circular arc. Now, like we usually do with these continuous distributions of charge, we divide the continuous distribution of charge into a large number, very, very large number of tiny little point mass elements, very, very tiny point charge elements rather. So we divide the entire charge distribution into very tiny charge elements. We calculate their fields and then do a vector summation of those fields. These fields are calculated using the formula for a point charge, and the vector summation is done by taking a summation of x, y and z components separately. Now, for calculating the field here, therefore, we need an element. Now, the element that we are going to consider in this particular case is located, let's say, at an angle theta and subtends at the center an angle d theta. And this over here, maybe I can highlight the element here. This is the highlighted element. This is the element for which we'll be calculating the field first, and then we'll be doing a summation. Now the length of this element, this length of the element will be the radius A times the angle d theta, and therefore the charge dq on this element is going to be charge per unit length times the length of the element, lambda a d theta. That's the charge on the element. Now we are going to calculate at this point here the electric field due to this element first, then a summation of those fields. Now the field due to this element at this point will be radially away from the element and will have a magnitude dE. This angle here is theta, so this is theta as well. And now dE will be dQ, that's lambda a d theta by 4 pi epsilon naught, divided now by the square of this distance of the element. Now this distance of the element from this point is a, and so we have square of a here, and dE therefore comes out to be, after a cancellation of a, we get lambda d theta by 4 pi epsilon naught a. So that then is dE. Now I'm sure you will recall some of the earlier examples where we used symmetry. We used symmetry with the circular ring, and symmetry can be used here as well. For instance, we have considered this element at theta and d theta. If we consider an element somewhere here symmetrically located on the other side of this line of symmetry, so this is the line of symmetry, we have this element at theta d theta. We take an element at theta d theta on the lower side here. This element will also produce an electric field of the same magnitude dE at an angle theta again. Now if you notice, if we call this direction as the x-axis and this as the y-axis, then the y components of these dE fields, the y components, these ones, they will cancel out. Why they cancel? Because they are exactly equal and opposite. dE sine theta, dE sine theta, these two cancel out. Those that are in the x direction will all add up because they'll be in the same direction. So dE cos theta plus dE cos theta, they all add up to give you the net electric field, which we now know will be in the x direction in this case. So this E net, the net electric field, now has to be in the x direction because all the y components are cancelled out. There are no z components. There are only x components which are all in the same direction. So E net will now be a summation of dE cos theta. We just have to add up the x components and we get the resultant field. The addition process or the summation of the x components is done by integration, and the limits of this integration are easily arrived at. You know, if you look at the elements here, the element at the lowest position here, this lowest element, for this element the angle theta will be equal to minus alpha, and for the element right at the top the angle theta will be this plus alpha. So for the lowermost element it's minus alpha, for the uppermost element it's plus alpha. So we have minus alpha to plus alpha, and so we've got lambda d theta cos theta divided by 4 pi epsilon naught a from minus alpha to plus alpha. This E net then equals lambda by 4 pi epsilon naught a. This comes out of the integration. Inside the integral we have cos theta d theta from minus alpha to plus alpha, and so E net now is lambda by 4 pi epsilon naught a times sine theta from minus alpha to plus alpha, and that then is lambda by 4 pi epsilon naught a sine alpha minus sine minus alpha. Now sine minus alpha is minus sine alpha, and so sine alpha minus sine alpha becomes 2 sine alpha, and so the net field now comes out to be lambda sine alpha by 2 pi epsilon naught a. That's the net field. So the net field is now pointing away from the circular arc here in case the charge on it is positive. If the charge is negative, the direction reverses, and that's true of all cases. When we discuss these fields for positive charges, we get a certain direction, and if the charge happens to be negative, the field will be in the exactly opposite direction. So that is a circular arc view. The next case that we are discussing is the case of a circular disk followed by an infinitely large plane sheet of charge. And now we move on, as I mentioned, to the case of a uniform circular disk. Now, the difference between a disk and a circular ring is in the fact that with a disk, the charge is distributed over the entire surface, whereas in a ring, the charge was distributed only on the circumference. So in a disk, the entire area has charge on it. In a ring, the charge was located entirely on the circumference. The radius of this disk is r, and surface charge density is sigma. The unit of surface charge density will be coulomb per meter square, charge per unit area. So this charge is distributed on the surface of this disk. We are interested in calculating the electric field due to this disk at a point whose x coordinate is x. The x-axis is the axis of the disk. Now, the axis of a disk is a line which passes through its center and is perpendicular to its plane. Now, since the disk has charge distributed over an area, the problem can get a little complex if we take tiny point charge elements, because there are kind of too many of them, and so the calculation would get more complex. Now, it can be done, but it is complex, involves multivariable calculus and stuff like that. You'll have to do a double integration, which is something you learn at college level. So it's an approach that we will not be using. We will use an approach that we can actually understand at school level. Now, what we'll be doing is, we'll think of this disk to be made up of lots and lots of rings. Think of a ring here, this one, for instance. Let's say it has a radius r, small r, and it has a width dr. Now let me shade it up, let me highlight it a little so that you understand what we are talking about. It's this shaded red area that we are now discussing. So this ring has a radius r and it has a thickness that's equal to dr. Now I make lots of rings like this, starting with the innermost ring of nearly zero radius, and then I draw another one outside it, and another one, and another one, and so on and so forth. If I draw lots of such rings, what I end up with is the entire disk. So I can think of this disk to be made up of lots of rings like these. Now, why I choose the ring is because if I repeat the ring large enough number of times, I can get the entire disk in the manner I just described. So what can now be done is, since we are aware of the formula for the electric field of a ring, we can use that formula to calculate the field due to one ring element, and then do a summation for the electric fields of all such rings. So let me draw this ring in this diagram. This diagram, of course, shows this disk kept in the YZ plane. That's why it appears like an ellipse. So it's kept in the YZ plane. The x-axis is the axis of this disk. Looking at the ring element that I've drawn here, over here, it'll look like this. Has a radius small r and a thickness that's equal to dr. So this is R, and the thickness is dr. Now let me take this ring element out of the disk and spread it straight, and the ring element then looks somewhat like this. It has a length 2 pi r and has a width dr. The area of this ring element, therefore, dA equals, this is a rectangle here, so the area will be 2 pi r into dr, and the charge dq on it will be sigma times the area. Charge per unit area times the area gives you charge, so 2 pi sigma r dr. That's the charge on the ring. Now the field, assuming charge to be positive, will be along the axis pointing away from the center of the ring. That's your dE here, and it comes out to be 1 by 4 pi epsilon naught. Now remember the formula for a disk, for a ring. The formula for the ring is Q. Now Q is 2 pi sigma r dr, Q times x divided by r square, actually small r here. The radius of this particular ring is small r square, plus x square raised to the power 3 by 2. This is from the formula for the ring, 1 by 4 pi epsilon naught q x by r square plus x square to the power 3 by 2. Now we'll be doing a summation of all these dE fields due to all the rings. The fields of all the rings are in the same x direction, so we need to do a simple summation. No components need to be taken because all vectors are in the same direction. When all vectors are in the same direction, we can simply do a summation without bothering about taking components. So 2 pi cancels and we have dE equaling sigma by 2 epsilon naught times, we can take the x out as well because that's also constant. The only variable here is r, so r square plus x square to the power minus 3 by 2. I take this from the denominator onto the numerator, and so the power becomes negative, followed by r and then dr, and we are integrating from 0 to r. Those are the limits for small r. If you're doing a summation for all the rings, the innermost ring has a radius 0 and the outermost ring will have radius capital R. So sigma x by 2 epsilon naught. Now see, the integral here is of the form fx, some function raised to the power n, times its derivative into dr. Now the derivative of this, the variable being r square, the derivative for r square will be 2r, and we have r here and not 2r. So we multiply and divide by 2 so that we now have a derivative of this quantity. And you will recall that form in integration, which I discussed in my video on integration as well. Fx raised to the power n times the derivative of fx times dx. When we integrate, we get fx to the power n plus 1 by n plus 1. So this is fx to the power n, f prime x, derivative of this function, followed by dx. So when we are integrating this, we get fx to the power n plus 1. Now minus 3 by 2 plus 1 will be minus half divided by minus half, and the limits are 0 to r. Now this 2 and this 2 cancel out, minus comes out here, and so we now have minus sigma x by 2 epsilon naught. Since the power here is minus, we have 1 by root r square plus x square, limits 0 to r. When we implement these limits, we get E equals minus sigma x by 2 epsilon naught, and inside the bracket we have 1 by, in place of small r, when we place capital R, we have r square plus x square minus, when we place 0 in place of small r, we get 1 by root x square, that's 1 by x. Now what we do is we take minus x inside the bracket and we have a field sigma by 2 epsilon naught into 1 minus x by root of r square plus x square, and that's your field for a circular disk. So the field will be directed along the axis, away from the center if charge is positive, and towards the center if the charge is negative. That's the field due to a circular disk. And now we move on to the next case, and that is the case of an infinitely large plane sheet of charge. Now what's an infinitely large plane sheet of charge? Think of this board and extend it infinitely in all directions. Now you extend this board. So now we are discussing the case of an infinite plane sheet of charge. Now we have an infinitely large plane sheet of charge with a surface charge density sigma. Then the symmetry of the situation here, this is this sheet. I've drawn a perpendicular distance a from it. Then the electric field will be perpendicular to the sheet and pointing away from it if the charge is positive, and if the charge is negative, it will be perpendicular to the sheet still but pointing towards it. Now that's something the symmetry of the situation tells us. Now, even though it looks like a kind of impossible derivation, I mean infinitely large sheet, how will we take elements and so on, but it's actually quite simple. You know, we already know this formula for the electric field of a circular disk of radius r at a distance x from it, where sigma was of course the surface charge density. Now if we think of or if we imagine or visualize a disk of infinite radius, we now visualize a disk whose radius is infinite, and if the radius is infinite, this term becomes 0 because the denominator is infinite. This becomes 0 and the field comes out to be sigma by 2 epsilon naught. So not much of a derivation there, very simple. We have arrived at the result. That is the field due to an infinitely large plane sheet of charge. So that's actually pretty simple. Now it's quite easy to solve problems which involve these results. If you are given a problem where there appears to be a combination of such charge distributions, then all you need to do is use the superposition principle and add the fields due to the various different charge distributions given to you, and add up vectorially, add up those fields to arrive at the resultant magnitude and also the direction of the electric field. I would thank you very much for watching this video and supporting this channel. Your feedback is welcome. You can always raise your queries in the comments, and I will be more than happy to answer those queries in the upcoming videos. So please do not hesitate to ask your questions in the comments section below. Also, if you're finding these videos useful, please like them and share them with your friends so that the message of this channel can reach a larger number of people. The message from me is that physics is kind of easy, but it can also be fun and can be learnt with the right amount of diligence. Thank you very much for watching.